All right. Good morning and welcome to this guest lecture. We have a really fascinating topic today on route optimization. We've discussed this in class, but when you think about it, when you're running 500 trucks, how do you actually allocate these trucks to all the different places that they need to go to and make that as efficient as possible? Over the years, this has evolved from people, and a lot of people, Martin will tell you, still do that, do that on paper with a pen, and it's a very involved and very cumbersome process, and you never get it right. But today you have technology, artificial intelligence, mathematical algorithms that you can apply to that, and that's what Martin will share with us. Martin is the founder and CEO of OmniOpti, which is a leading provider of route optimization in Europe. It's a startup. He's working with some really, really big name companies in Europe. And, he's graciously agreed to talk to us this morning. So Martin, give us a little bit about your background, and then, you can launch right into your presentation. And thank you for being here.
Thank you for inviting me. It's really a pleasure and an honor, and always happy to spend time with you, and also to share some of my experience with your students. So my name is Martin Pečar. I am from Slovenia, Europe. Mathematician by profession, and optimization is my passion. So I've always tried to do things in the best possible way. I started my career in a vehicle tracking company where I developed some algorithms or methods to compute the road network out of the GPS tracks. Then we've done also speed profiling and time-dependent routing and so on, route optimization. Then I worked for a North American company dealing with route optimization. Then also went back to academia a little bit to do some further research. And I was even running the cluster for smart cities in our country for a while. And eventually I founded my own company because I developed a new algorithm for multi-objective optimization, which I will also discuss today. So hopefully it will be interesting for you. I will also ask you a few questions, so I'll be happy if we made this session interactive. I'll be really happy to hear more about your experience and maybe challenges or thoughts on the topic. But let me share with you what I have to say. Okay, Chris, maybe just if you enable screen sharing. Okay. So yes, I'll be talking about this new dimension of route optimization. So why would you care about route optimization? Well, because bad planning costs money. Local logistics globally spends over $300 billion each year. So that's a huge number. And even if we can save just a small fraction, like a few percent of that, it has huge impact on the economy. And not just economically, but also ecologically. So also decreasing the impact on the environment is something that we should strive for. Okay, I guess you are familiar with route optimization. So do you have any thoughts or ideas or experience? What are the biggest problems in local distribution, home delivery processes, and so on? What are people struggling with? If there are any thoughts and ideas.
I would just first say, I guess, just utilizing your assets to the most capacity available to you.
Mm-hmm. That's for sure, absolutely. The, let's say, issues that somehow I am noticing most frequently is the fuel prices. So this is something that is quite significant. and also lack of drivers. So these two problems and challenges are always present, I would say, and especially in the peak season, like right now, between Black Friday and Christmas. Everybody wants to get their presents back home as soon as possible. So it's a huge strain on the supply chain. So the classical route optimization problem looks like this. So you have a distribution center, a lot of locations that you need to visit, and some resources that you can use, some vehicles. And you have to decide who will go where and what's the sequence going to be. And mathematically speaking, it's quite difficult problem. I apologize, I will talk about some basic mathematical properties at the beginning, just to give you an understanding of why it's really so challenging. So the underlying problem here is the traveling salesman problem, which is dealing with the ways how to visit several locations. So you need to visit each location exactly once, and how many ways are there to do that? So if we have 5 locations, do you know how to compute that, all the possibilities, or at least have a hunch how many options there are? Have you been discussing that in the past or not yet?
I mean, it would depend, I guess, again, on assets. Like if you had 5 trucks, you could do like a point to point, but like if you had
No,
one vehicle, you would have to do
just one.
Okay, just
Just
one
one, you have
vehicle.
to do the cycle.
Probably go out the furthest distance and work your way back in.
Okay, that's probably a good approach how to do that. But let's say, how many different options are there to visit 5 locations? Or maybe just a hunch.
25.
25. Okay, that's probably 5 times 5, right?
Yeah.
Okay, that's a good guess. However, well, let's see how we get to that. So let's say we want to spell out the sequence, and first we need to decide for the first location that we visit. How many options are there for the first location?
1.
Well, no, 5, because there are 5 locations, so we have 5 options. We can choose any one of those, right?
Oh.
Yeah. So for the first location, we have 5 options, and we've decided for 1. So how many options do we have for the next one?
4.
Yes, because we've already used 1, and there are 4 remaining. And for the third one, how many do we have? 3, yes. And for the fourth one, 2, and for the last one, only 1. So the number of all the possibilities how to do that is 5 times 4 times 3 times 2 times 1, which is 120. So 5 times 5 was a good guess, but actually the number is much bigger. What about if we have 10 locations? Do you have a hunch how much that might be?
240.
240. Okay, thank you for your guess. Of course, it's bigger than in this case, but it's actually way bigger because it's 10 times 9 times 8 times 7 times 6 times 5 times 4 times
3.6 million.
Absolutely, yes, yes. So for 10 locations, we have over 3.5 million options how to do that. Of course, not all of them make sense, so you can throw away a lot of them right from the start. However, there are still a lot of them that might be good. So if you want to find the best option, you practically have to check all of them, or at least a large portion of them. At least go through all of them, and some of them you can cancel right away, but for some you have to also calculate the whole distance or the whole cost to be able to compare that to the best previously found solution. So it's quite a lot of work, right? I wouldn't want to do that manually. That's for sure. And it's, like playing chess. Also, in playing chess, there are millions or billions of combinations, and we know that the world champion in chess was beaten by a computer decades ago, and since then the computers became much better, and the programs also much more efficient. So humans, we don't stand a chance against computers in these kind of problems. The thing is, have you ever heard about exponential function? Maybe during the COVID, when they said, oh, the number of people who have the disease can grow exponentially. It grows really fast, but the factorial function, so this with the exclamation mark, this function here, it grows way faster, because at the exponential function, you multiply with the same number, with the same value on each next step. Meaning, for example, times 2, times 2, times 2, times 2, if you double, for example, every day. In a factorial function, you multiply with a bigger number at each next step. So that means like times 5, times 6, times 7, times 8, and so on. So it grows faster and faster all the time. And that's why this, we call it combinatorial explosion, is so huge, and it's really difficult to find that to check all the solutions. It's impossible. For small problems, people have done that in order to gain some benchmarks, but it might take months to compute that. But for the large data sets, it's impossible. Well, things get worse. Because in real life, you have also additional constraints, like time windows. For example, you need to come at a certain location between 8 and 9 in the morning. Then you have vehicle capacities. You cannot do everything you would like to, because vehicles get overloaded. It can be due to the volume, or because physically you can't get things in, or due to weight, there's a restriction on weight, or even perhaps value. For example, for security companies, you have a limit of the value that you can transport in the vehicle due to insurance companies and so on. Then you have location accessibilities. You might not be able to visit all the locations. A location might be in a small town with narrow roads, and you cannot arrive with a truck and trailer. You need to have a small truck or even a van to service it. And also, usually there are several routes, several vehicles, which makes the problem even more complex, because you have to determine the area, or at least select the locations that will be serviced by a single vehicle, and these can be shuffled, so the number of options get overwhelmingly huge. And all that.
Are there certain constraints compared to the European versus like the domestic model over here in the United States that y'all deal with?
Well, there are differences. For example, here in US, you have way more restricted areas, like gated communities that you kind of shouldn't be going through. And then it's also some additional problems regarding accessibility into those locations and so on. Then here in US, right turns are preferred, because in most junctions you can turn right even if the light is red. In Europe, you're not supposed to do that. So there are some small differences, mostly regarding the routing procedures generally. However, this route optimization process is generally quite similar. Well, there are some differences regarding the driver working time restrictions and so on, but these are dependent on each country. Okay, And the way route optimizers work is they are usually using some meta heuristics plus simulated annealing. So what is that? Heuristic is a method which is usually working good. You can't really guarantee the performance, but usually it works quite well. For example, the one that you said, first start with the most distance locations and then come closer to the, so selecting the locations on the route this way. This is one of the heuristics. Another one might try to, let's say, minimize the number of vehicles, or some are focused on the working time, some on the cost or distance, and so on. And meta heuristics means that you have several heuristics and you shuffle them. For a while you use one of that, for a while the second, then third, and so on. So you mix them during the process of optimization. And simulated annealing is trying to get to a better and better solution. So imagine if you would be on a top of a mountain and you want to get to the sea. What would be your strategy? So one of the possible strategies is that you go downhill all the time, or perhaps even choose the route of steepest descent, so to get down as soon as possible. However, in this case, you might get trapped in a mountain valley with mountain lakes and so on, because there's a local minimum, but there are better solutions somewhere elsewhere. But if you always go just down, you might get trapped in a local valley. So therefore, the simulated annealing usually allows some solutions also to be a bit worse, in order to allow you to escape from this local minimum, to cross a pass and get to the sea eventually. So this is the usual approach that route optimization solvers usually take. However, due to the problem mentioned before, so this combinatorial explosion, there's no guarantee for the optimality. If somebody will say to you, we can provide you with the optimal solution, they're either lying, or they don't understand the problem, or they're just oversimplifying. Or perhaps in a couple of years they have a quantum computer which works in a different way and is really able to process huge amounts of possibilities. But generally, you have no guarantee from the optimality. The only thing that you know is, or the best thing you can get is, you can get an approximation of the best value. So you can say, okay, what I found is within a certain factor of the best possible solution. Also, the more time you invest in the process, the optimization, the better are the results, because you're checking different options, and the more options you check, the better the solution you'll get. And usually this route optimization saves 10 to 30% of the costs compared to, let's say, manual route assignment. So let's take a look at how this works in practice. Okay, I'll show you a tool, and here's a synthetic case of deliveries that we need to do. So let's check it at the data. We have, just a second, altogether, I think it's 150 stops, locations that we need to serve. And for each one, we determine, of course, the coordinates. So where do we need to make that stop? The service duration, so stop time. This is also quite important issue. You want to have that as accurately as possible, because just a few minutes of difference can make really a huge difference in the quality of routes. And of course, if the number is too small, then your real routes will not resemble your plan at all, and you'll have plenty of problems. So try to get this as accurate as possible. Then we have the time windows. When do we need to be at a certain location? Quantity, which can have, sorry? Yeah, okay. Then we have the quantity in several dimensions. And then we might have also some other required skills or properties, like maybe a certain vehicle needs to arrive, or certain type of vehicle or driver, and so on. Okay, then we have also information about the vehicles. So the vehicles are also, we state where they start and where they end, the availability time, the capacity in various quantities. That might be, for example, volume, weight, number of pallets, or something like that. And then we have costs, like per kilometer, per time, so on, fixed cost to use that, a number of vehicles of that type. So how would you approach this problem? Or you have any ideas how many vehicles, how many routes you would need to use for that? Or how would you approach that kind of problem?
Where are they centrally located, like the starting point at?
Mostly I think one is here and three are over here. So yeah, this is not depicted properly here, but yeah. So the two are here and three are here.
Ooh.
Yeah, it's a difficult problem, absolutely. Usually, this has been solved in a way that you have some fixed areas, and you say, okay, if location is in this area, then it's going to be serviced by a certain vehicle.
I guess if I remember right from class, you would want to like kind of loop them out and kind of break them into segments, kind of like how a flower looks. Like each of them like cover, let's say 4 or 5 area, and then the next asset would cover another 4 or 5 area, or however many, and just kind of loop them back in a kind of a repetitive circle in certain areas. At least up near Dallas, down low, I guess that would be kind of like a point to point, like go down San Antonio and back with a couple assets.
Yes, that's a great comment. Absolutely, I agree with that. Well, my approach solving this is pressing this button. And then we see within a few seconds, we already have a solution and the initial price. And this price is usually something similar to what a dispatcher would do. So it's a kind of a simple heuristics. And now we are trying various options. Now we've checked over 4,000 options already. Oh, and now we see the price has started to decrease. So this is kind of a step-like procedure. Every now and then you get some improvement, but it's really difficult to predict that because there's some randomness in the process. And usually it's like this, maybe in a problem of this size or a bit bigger, perhaps you can save about 10% in, let's say, half an hour, and then you save additional 5% in maybe a couple of hours more, and maybe 2% in a couple of days. So the curve goes like this. At the beginning, the improvement is quite fast, and then it slows down. And it means that probably you're getting close to the optimal solution. But of course, as mentioned, we don't know what exactly is the best solution, but we're just kind of assuming or hoping or guessing that we're getting close to the best one. So the quality of different route optimization solvers are mostly in that how fast do you get to a very good solution. So for example, different solvers can tell you how much money are you able to save within 30 minutes. For example, right now we're preparing a call for a tender for a post operator back in Europe, and one of the requirements is that they will give sample data to each one of them, and they will have to compute the result within 30 minutes, and then they'll compare the results and do their selection based on that. So, okay, we see that we've already, I think we saved about $150 right now, 40,000 options that we checked, and we have 14 routes, and all of them, all of the jobs were assigned, so that's good. But when you don't have time, you simply stop. Okay, we'll have to start doing that, and here we have the routes. What's really nice is that you can check all the information, like we have Gantt chart, and you can see how each route will be, what's the process. So you can say, okay, this is the blue is traveling to that location, this is stop time, and red is waiting at some locations perhaps. So you have all the information about the planned process. You also know, for example, the utilization of the vehicle, so how is it loaded. I think the capacities are between 5,000 and 7,000, so this one is loaded quite well, and most of them are also quite full. One more thing, sometimes the transport operators say, oh, I can't improve anything, my trucks are full, and this is the best we can do. That's also far from true. Well, it's good that the trucks are full. However, you can drive around the city all day long with a full truck, and that's not efficient. So that's one of the KPIs, but not the only one. And we can see that one or two of them are also quite empty. But the problem, the reason is because, so these are these routes. And this one with only 2 locations, you can see it takes the whole available day. So they're not sleeping or slacking, but really the problem is this way, that it can be better. And this kind of tool really enables you to do forensics on the routes and inspect and find out the reasons why something is done this way. And as you mentioned, the loops, also we can see here that usually the routes are not geographically separated. I also often see that, of course, there are loops and they're kind of overlapping. For example, this one, the purple and the green one, and these two also, and maybe these. So we can see that strict separation of the areas usually don't bring you the best possible route. It's generally good to have at least maybe some area when the some overlapping area where these locations might be serviced either by one or another vehicle. However, one surprising thing that I've experienced a couple of times is generally the less constraints you have, the better is the final result. However, sometimes when you add more constraints, you can get better result in a shorter time, because you simply, the space of the possible solutions is smaller, so you are faster to converge, to come closer to the optimal solution within a shorter time if you have more constraints. So it's not a rule, but it's something that I've experienced a couple of times, and it has surprised me also, but that can also happen. Okay, that's a little bit of my wisdom regarding this. Any questions?
My only question is, I mean, I just noticed, I mean, typically you don't want, cross passing or anything like that. And I just see that down here kind of on the south side of Fort Worth, You have that green and that purple kind of overlapping the same area.
Oh, this one.
To your left. Yeah, kind of right there.
These.
Yeah.
Okay. Well, this is not so much of a problem. I think it's more a problem if the same route is doing some zigzag, back and forth. It's crossing itself. The loop is crossing itself. But if two loops are kind of intertwined, I think that's not a problem, because it's more about the single route being effective, and sometimes due to the road network, simply this connectivity is different than what we see with our eyes, like the geographical density, something like that. That's been my experience. I've seen this, and for example, this and this overlapping, and these two also. I've seen this kind of behavior quite often, so I believe that that is close to optimal. I can't guarantee that that should not happen, but this is somehow my or that it's really better that it does than not. I think it mostly depends on the road network topology. So how the roads are connected, because sometimes it's much easier to do a smaller loop than just do something which would guarantee that you are geographically somehow together.
Okay.
Okay, perfect. So yeah, let's move on with this presentation. Yeah, we've seen this is the schematics of this classic route optimization, and we've seen how that works. And there, is there a question, Jeremiah?
Yes. Hi.
Go ahead.
I just wanted to for the optimization solution that you clicked on in that program. Looks very amazing, honestly. But does that put any considerations at pickup and deliveries? For example, the space of that truck, and if your pickup something, does that consider the size or just only visitations of that sites?
It takes all the relevant information into account. So time windows, stop times, capacities. So for this particular solution solver, it's not. It doesn't consider, let's say, the way how you stack the parcels or whatever, but it considers summing the value. So, for example, one parcel is 1 cubic meter, another one is 2 cubic meters, and then it sums to 10 cubic meters, and the capacity is 12. So that's okay. And another dimension is weight. Like you have 50 kilograms plus. So if you sum up all the items, cargo items on board, you should not exceed the total capacity of the vehicle. So we have 3 dimensions, which might be, let's say, volume, weight, and number of pallets, or something like that. Okay, and it also considers pickup and delivery. I've just shown this simpler case here where we only have delivery stops, meaning that we distribute from the distribution center, but it can be easily also used for, let's say, parcel deliveries, or even, let's say, shuttle transfers or something like that, where you have pickup and delivery points, and you have to take all that into account.
Perfect.
So yeah, you can, if you have some specific problems or challenges, you can also contact me directly, and we can check if that can be done.
Is traffic patterns like peak and low times ever considered in the constraints or how you configure your routes?
Not in this case where I showed it, but of course it has to be. Yes.
Okay.
Because that makes a huge difference. If you are have a route going into the city when the largest peak, largest traffic jam is, you'll lose half of the day just because of that. So absolutely, that's one of the critical components. I totally agree. Okay, so here we have a schematic representation, but most of the classic route optimizers assume that there's only one connection between each pair of locations, which is usually the fastest route. That's a good strategy because this way you can pack the most locations on a single route. However, it's not always the most efficient because the fastest route, the red one, can be quite long. On the other hand, if you would say, okay, let's take the shortest one, then that might take too much time. But sometimes there are options somewhere in between, shorter than the fastest and faster than the shortest. I also used to work for another route optimization company, and we had a meeting where we were checking plans versus execution. Of course, the plan was usually better. Just in one case, execution was better, and I was really baffled. And I asked my colleague, so how is that possible? This guy did a better job than what we did, and it's such a complex mathematical problem. And he said, well, you know, he didn't drive where he was supposed to. He took a shortcut. And I was, well, why don't we always suggest shortcuts then? But it's not that simple. Also, for example, Google Maps. This is an example, my personal example. I live here in Ljubljana, that's the capital of Slovenia, and my wife's family, they have a wonderful wine making farm on the border with Italy. And we were visiting them often, and Google always suggested this route on the freeway, which is obviously way longer. And we often took a shortcut through the hills. That's also where the old Roman road used to go, which was way shorter. It just took a little bit more time. And Google Maps never provided me that option. And this was really frustrating. And therefore, I developed an algorithm which can provide these kind of options. So instead of only one connection, we can now provide a lot of paths between pairs of points. That actually adds a new dimension to the problem, which makes it even more complex, even more difficult. However, we've seen that we can find better solutions, that we can boost the performance of the classic optimizers by up to 40%. So how is that done? For example, these dots represent paths. This one represents the fastest, this one the shortest, and these are other options in between. So for example, if you go from point A to point B and have a time window when you need to arrive to that location, and for example, it's somewhere here. We need to arrive at this time. So the best option is to choose a path which is the shortest within the time window. And this is the distance that we're able to save. So luckily, all the other providers, they're focusing on single objectives. So either the fastest or the shortest or the cheapest or whatever, but still it's just one objective. So you're quite limited to what kind of results you might get. On the other hand, we provide the whole Pareto front of the options, and therefore you have larger space to choose from, because sometimes you're not even able to determine in advance what's most important for you. And sometimes just when you see the various options, you say, oh, this might be better. You know? And therefore it's good that we can provide a lot of those options. And it's not just about time and distance. It can also be cheapest, lowest emissions, safest, and so on. And there are a lot of problems that are not even directly, that you cannot really directly put a number to that. But still, if you can decrease that, there's a lot of value hiding in there. And so far, we've demonstrated that if we're trying to reduce the distance and fuel usage and emissions, we can save 5 to 15% compared to using the fastest routes, which is globally has potential of 5 billion savings per year. And here's an example also here in close to Texas. You can see different options. I'll also show the real live demo later on. One more thing is there's a sweet spot, let's say 3 to 30 miles between stops. I think here is even more, but for example, this doesn't make sense if the stops are really close to one to another, like every block, because you don't have alternatives. Or if you do 1,000 miles, there's probably 1 or 2 interstates that make sense. But for some local distribution and home deliveries and so on, this really makes sense. Another thing which is important is if you have more options, which route to take, this decreases the predictability and increases safety. So we started to call this stealth routing. This is especially important for security companies. For example, a cash transfer, or even maybe a transfer of artworks, or maybe also like wine and spirits and so on. Or maybe transfers of some high-profile people, either politicians from their office to the airport, or criminals from the prison to the court, or something like that. So this, we've identified some additional added value that's on the top of just reducing the distance and saving on fuel costs. Also, another case where this might be quite important is, for example, extra large bulky transports, meaning, let's say, some fans for the wind turbines or something like that, or for some power plants, some big parts. You cannot drive that anywhere. You have to be aware of, let's say, the sizes of the roads, the heights of overpasses, the weight limits of the bridges, and so on. So this multi-objective optimization can also be useful in that kind of cases. So yeah, like, stealth routing, if you have a lot of options, you're less predictable, and if somebody wants to attack you, they'll have a much harder job. The good thing is also that these two problems can be somehow decomposed. One is, so the classical optimization is dealing with the sequence of the locations. This is also a very nice example. If you follow the red arrows or the green arrows, the difference is about 20%. So you do the same amount of work. Your truck is full in both cases, but the costs are very different. Of course, in this case, it's obvious. We're not stupid to do that. But when you have hundreds of locations and time windows and other constraints, this happens really often. So this is actually the way how the benefit is gained, reducing this kind of crossovers within the same route. And when you have the sequence specified with the classical optimization, then the other add-on of alternative routes can choose the right paths, how to go from point A to point B. So not necessarily only the fastest route or whatever, but we can find, we can provide a lot of those options and select the most appropriate one given all the other constraints, like time windows at all the locations and total working time and so on. And we've seen that we can save additional 5 to 15% on the top of the classical optimization. So even if somebody already has a classical route optimization solution provided by somebody, we can still deliver something on top of that. And the process flow doesn't need to change. It's first, of course, you collect all the data, then you do the classic optimization, and when the delivery sequence is set, we do the multi-objective optimization, and those optimized alternatives can then be sent, for example, to the mobile app of the driver. And this way, we can really, the process flow practically stayed the same. All of the tools, which people also get used to, stay the same. Just the bottom line is improved. It's like, you know, having a nitro booster in the engine. And our business model is also software as a service, so there's no, let's say, no huge investments in the beginning. And the important thing is the modules can be easily integrated with via API. Okay, let's check an example for a truck. Let's say annual total cost of operations are about 70,000. Do you agree with that, or do you have any ideas? More or less, this might be a bit old number, which means about $200 per day. And classic optimization saves an average of $30 per day, and alternative routes can save additional, on average, $10 per day. So with one truck, it's not much of a big deal, but let's say we have 100 or 1,000 or 10,000 trucks, then it becomes, these numbers become quite large. Okay, the industries where this is important are retail, of course, mostly for the internal distribution, but possible also home deliveries, of course. Then distribution, like hospitals, restaurants, catering, pharmaceuticals, food and beverage, and so on. Home deliveries, but perhaps especially larger items like furniture, building materials, and so on. For the smaller, for the letters or smaller parcels, you might have really high density. So the classic route optimization also is very useful, but these alternatives perhaps a little less. And again, security is also one of the industries where this is really crucial. Of course, it's not just about transport of cargo, it's also about transport of people, so mobility, shuttles, ride sharing, or paratransit, or something like that. And also traffic management might benefit from this. So right now, traffic management, Google Maps practically controls the traffic. And they send everyone through the fastest route, and that gets usually clogged. Then they send them through one detour, that gets jammed, and another detour, that gets jammed, and so on. If traffic authority or Department of Transport or some local authority would have its own navigation app, they could see where the people are going, and they can distribute the traffic flow in a more efficient way, like sending 50% of the traffic through the traffic artery, 30% through one detour, and 20% through another detour in advance. And also modify the traffic lights in order to accommodate that traffic flow, in order to minimize the traffic jams. I've discussed this regarding the road transport. However, the same algorithm that we have developed could also be used in another domain. Perhaps in logistics, it would be terrain, like off-road navigation, or navigation on water or in air. In the last two cases, of course, the weather is the most important issue. So these are, let's say, possible additional usages. And even more, outside of logistics, it can be used for optimization of, I don't know, data networks, printed circuit boards, design, or finding a good place for infrastructure like roads or pipelines and so on. So there's a lot of possibilities and a lot of benefits that could be brought through this. So really, I thank you for your attention, and I invite you to really be curious and always try to somehow challenge the status quo and try to find better solutions to things. And hopefully also our new dimension of route optimization can contribute to that. Okay, any questions perhaps?
Thank you, Martin. This was fantastic and very insightful, right? It's so good to see this in practice as opposed to just in a textbook. One of the questions actually that I had, I'll kick it off, and obviously anybody, please just jump in and ask questions. But how do you build a career in kind of the optimization of supply chain problems? How do you, what is your advice to get into this field for students specifically?
Cool. That's that's a very difficult question. Mathematical questions are much easier to answer, I think. Well, the question would be find the problems. Talk to people and try to find out what the most pressing problems are, and then try to solve them. Very often, especially more technical guys like me, we see a technical solution and we try to develop this and say, okay, the whole world will just love it when it's done. And it's not always the case, or actually it's rarely the case, I'm afraid. So try to really find the problems, people with problems, and then you'll be able to find the solutions. Because creating a solution is, let's say, relatively easy, or finding a solution is relatively simple. There are so many tools around the world and so many people that are skilled in that. And also, let's say, AI now is giving us a lot of options and a lot of tools how to manage things. So if you want to be successful, I would say find the problems first and then look for the solutions.
Yeah, thank you. Good. Yeah. Another question, tying into something that you said earlier, you said, that, and this is really interesting. Oftentimes you also need to optimize for the safest route, not just the fastest, cheapest, or shortest. And how do you establish the safety of each route? Kind of what data do you use underlying this to make those decisions?
It also depends on the client, because we can tailor things according to their wishes and their needs. However, the safety can be either perhaps like maybe numbers of accidents in the area. So you want to avoid areas where there have been many accidents in the past, or generally maybe areas where there's crime, maybe some neighborhoods or something like that. Then you might want to avoid also the areas with a lot of traffic lights where you might need to stop often. That might be a problem. Or perhaps in one case I remember it was a distribution company, and they said they wanted to avoid winding roads because their packages might tumble and break and so on. So they preferred straight roads with least acceleration from either direction. So all of that can be handled. It's just important that you know what's actually important for you, and then you can find a way how to describe it with a number. Trying to find some databases or some way how to put it into numbers.
Interesting. Yes. So another thing that I found interesting, you mentioned on in your answer to Christopher's question earlier that in the US right turns are preferred because they're fast, and you don't have to wait at a red light for a turn. And UPS obviously was, I'm sure this was really famous. They started to build their algorithms around just making right turns wherever possible, and they saved huge amounts of monies, in the hundreds of millions of dollars every year. How and then they moved away from that, right? And they started to bring in other constraints. What is your view on, how do you develop these solutions with your clients over time, over a period of several years? Do you regularly go back and say, hey, we've got some new insight, and now, right turns aren't actually the only game in town anymore. There's other things you need to consider, and we can save you an additional, whatever, 5%, 10%. How do you work that with your clients?
Of course, every product needs to be constantly developed. It's a never-ending story. However, let's say the basic mathematical background remains the same. If an algorithm works, it works in all cases. Like finding the shortest path, that works on every network. However, the question is more about the parameters that you put on the network. So what are the objectives that you try to optimize on, and what are the databases where you get your data from, and so on. This has to be constantly updated and improved, of course, in connection with the clients. You always need to listen to the market, to the users.
Yeah. Okay, thank you. Anyone else? I keep asking questions here. Anyone else who would like to?
Oh, there's a hand. Selena.
Yeah.
Selena.
Oh, hi there. I guess my question is going to be with last mile deliveries and stuff, when you're using like electric vehicles and stuff, does the route variance, is there a larger amount of routes that you, for instance, with just electric vehicles, comparing it just fuel, just regular fuel vehicles?
Okay, I'm not sure I understood the question very well. So
Is there-
what's the difference between the electric
Okay,
and
yeah.
internal combustion
So
engine?
for electric and then regular like diesel or gas, for the last mile deliveries, is there more options compared to just doing fuel?
I would say there's less options because the range is lower, and also there are less, typically so far, at least I would say in Europe, there are less locations to charge it. So you're a bit more constrained regarding this. However, it's true that there are some areas which are allowed only for smaller vehicles and also electric. For example, some, especially I would say in Germany, some centers of some cities are closed down for diesel vehicles, especially the older types. So in this case, this area some areas can only be accessed by electric vehicles, especially if you have some smaller, like e-cargo bikes or something like that. That, of course, the network which is available to those kind of vehicles is, of course, larger than what you can access with a large truck, especially if it's internal combustion, dirty truck, let's say. So there are let's say two layers of that. One is the areas which can be accessed, and this for the city centers, it seems that electric vehicles have more accessibility. But on the other hand, the general, let's say, options or possibilities of an electric vehicles are characteristic at the moment are still worse than.
So essentially the
Okay.
infrastructure is just not in place to support it as well.
So they
Yeah.
have more constraints.
Yeah. And also the routes need to be shorter. For example, you can't have 400 miles done with an electric vehicle, or mostly not. Well, you can do that with an internal combustion. So at least much easier.
Okay.
Yeah.
Thank you. I appreciate you answering.
Thank you for the question. Also, one of the things, do we still have a minute or two, Chris?
Yeah, we do.
Okay. For example, once we did a project in Florida, and because it's so narrow and long, practically half of the day was used just to get to the location. So not a lot of work could be done. Our initial idea was to somehow to prolong the routes, but in a way that the drivers would swap, so that you could just take a car and go to a location and swap the drivers and continue with the route. They didn't really like this idea, but eventually they used multi-day routes eventually, which of course had huge savings for them. So very often when you look at something, you get an idea on how to modify it or improve it. Very often, I think the best thing is just to have a set of fresh eyes, because the one that's working there for 20 years is used to that, and it will not see any other options. But if you come from outside, you see practically everywhere I've seen inefficiencies so big that I could cry sometimes. But yeah, that's the way it is.
Yeah.
Okay, maybe just to show you also this live example. So this is the fastest route, and this is another option, and you can see the difference is just 1 minute and 3 miles. So you can gain 3 miles and lose just 1 minute. That's an example of why this is useful, and you can have this for different vehicle types also. So yeah, just to get a understanding of how this might look like.
Yeah. Thank you. Very
Okay.
good. Well, thank you very much, Martin. This was really, really great. Really appreciate your time. Yeah, thank you so much for this, insight into your world, which is certainly
Thank you.
complex, but also something that everyone here on the call will encounter sooner or later in their career. This is coming in major ways. It's not widespread today, but it will be, and it'll get better and better.
Okay, wish you all good luck and plenty of success.
Thank you.
Thank
All right.
you.